Not
Yeah.
excited.
But I was worried about doing it another day because I usually get to do it.
Yeah, no, that's okay.
But we won't know for sure for 3 weeks.
Dan here? He's gonna come late, I think. I think he has to run from somewhere else.
Okay. I think if we're allowed, are we allowed to get started without him? I think we can. Myra's online, right?
Well, you might not know, but she
I
said
don't
she'd be
know.
online, so we just
It'll
keep.
be up after the fact too. People can watch it later.
They're allowed to work, yeah. So, well, we'll start without Dan, he'll live.
So currently, nobody but me on your committee is here right now, but that's all right. Okay, so I am just gonna get started. So I'm really happy to be able to introduce Marissa Tripus to all of you today for department seminar. I imagine that most of you need no introduction to Marissa, since, you know, she kind of is pretty well known in the department. She's hugely active in the department, whether that's through the GSA, basically halfway running the REU, mentoring a bajillion undergrads, including many of them in my own group. Ivana, I see you back there. She's always doing lots of things in the service realm because unfortunately she's a bit like me. So for better or for worse, right? But nevertheless, if you don't know, Marissa grew up in Pennsylvania and she came to my group in 2022. And after graduating from Millersville with her BS in meteorology and oceanography, right? So she kind of thinks about both of those realms. And so I remember kind of in 2021 when I kind of first met her over Zoom. Angel was coming into my office. I was getting off of a Zoom call with her, and he kind of looks at me and he's like, "I think you just found your first graduate student." And turns out that he was right. So in the 2.5 years that Marissa's been here, I have time and again really been struck by her kindness and her courage, right? Being someone's first graduate student is a uniquely awesome, at least that's what I tell myself, and uniquely burdensome experience. Because in addition to weathering the ups and downs of your own learning process, you also need to weather the ups and downs of your advisors, right? Because we have to learn how to do things as well. And so in Marissa's case, the weathering was that we didn't really fully settle on her research project until the very end of her first year here, right? And so for some perspective, we both started out thinking that she was going to do Arctic oceanography. The Archean is not the Arctic, all right, in case you did not know, all right? So we changed things up a bit. So thankfully for both of us, we're each as intrepid as the other, and we decided to dive into early Earth oceanography, all right, which is something that I've really been interested in for a long time but never gotten around to doing. And I also know nothing about it, okay? And so Marissa has really had to guide the research in this project, right? Including learning how to set up and run a climate model that I also knew nothing about, all right? On the university's HPC resources, which I also knew nothing about. Seeing a theme here, right? And so what she's done here is really quite impressive, having to kind of grapple with all of that in addition to just figuring out how to do research, right? In a good way, right? So the last thing I want to say is, though, is that when I advise, it's really easy for me to lose sight of the big picture by over-focusing on what needs improvement or what could be done better, right? We all do that as advisors, right? But today I just want to say to you, Marissa, that I am incredibly proud of you, all right? And it's my hope that after you finish with this talk that everybody else in this room is going to be incredibly proud of you as well, all right? And by hope, I mean you better. All right, so without further ado, Marissa, the floor is yours. Well, thank you for that, Hannah. Can everyone hear me okay? Sweet. So as Hannah said, today we're going to be talking about the ocean and a little bit about the climate of an Archean-like planet. And to start, I want to kind of familiarize everyone with what exactly the Archean is where we are in geological history. So what you're looking at here is a geological timescale where we have modern Earth here, and as you go inward in the spiral, you end up at the formation of Earth about 4.5 billion years ago. And to just make it a little more clear, here we are. But there's a lot of big milestones that have happened on Earth. There's been a lot of events that you can probably think of. One of the first ones we all probably think of is the dinosaurs at about 245 million years ago. Maybe even the first tree at about 360 million years ago. And even maybe the first fish at about 530 million years ago. But if you notice, we're still very close to where humans are in this time period, in this time scale. So to find the Archean, you actually need to keep going inward, and eventually you'll end up in this little bubble that was about 4 to 2.5 billion years ago. Within the Archean, there's a lot of big events going on, so I'm going to highlight a few of them so you kind of understand what's going on in this
environment. To start, at about 3.8 billion years ago, there's believed to have been the first ocean forming on the planet. We also are seeing the first DNA. So the Archean is believed to be the eon where life was forming on Earth, which is kind of cool when you think about that happened so long ago. We also have our first continent forming, and I will get into that in a little bit as to what's going on with that. And the end of the Archean is marked by the Great Oxygenation Event, which was the huge influx of atmospheric oxygen into the system because cyanobacteria was present at this time. But why do we actually want to look at the Archean? And there's two main reasons why we're doing this. The first is to understand the formation of life on Earth, but to understand that, you need to understand the environment of which it came around in. So that's what we're getting at in our first half, is just what is this environment that we see life popping up in? But the second is we're trying to use it as a test bed for considering oceans when you're looking at this habitability question of if life can be on other planets. We know oceans play a huge role on our planet, so why wouldn't they apply the same principles to other planets out there? And you'll see, this is coming up more recently in literature. This Olson et al. 2022 paper was a really nice dive into that, where essentially this paper looked at how different ocean properties will change under different planetary and environmental parameterization, and then how this could ultimately impact what your planet's habitat look like. And then if you notice in my title, I said Archean-like, and that plays a huge role in this, is I'm not modeling one set time in the Archean. It is 1.5 billion years. It's a lot of time to cover in a model run. So instead we would use the Archean as a way to create a different environment to look at what could be going on in a climate system when you change a lot in. You'll see in the next couple slides why it is a very different environment. So to start with what's actually going on in this environment, when you start looking at any paper on early Earth and deep time paleo work, you'll run into this faint young sun problem. And this is really well depicted in this figure, where we have time on the x-axis, where we are over here, and then we have the solar luminosity relevant to today. So over here on modern times, we have 100% the solar radiation, but as we come further back to the Archean, we end up about 75 to 85% of how much energy was coming from the sun, because the sun is a lot younger when you go back billions of years. It's not producing as much energy. We're getting less incoming solar radiation, which then actually will act as a cooling mechanism on your planet. But when you look at what's going on in the atmosphere, you actually can see that if we have modern concentrations of what our greenhouse gases look like, and this dashed line is the freezing point of seawater. If you have modern concentrations of greenhouse gases, our planet should have been entirely frozen until the end of the Archean. However, based off proxies that we have, we know that this wasn't the case. And when you actually tune the greenhouse gas to what it could have been, and it's a lot higher concentrations of stuff, you actually will counteract what's going on in your faint young sun problem. You'll still end up with a liquid ocean because you are now warming your atmosphere with these greenhouse gases. And just to kind of show you how variable this environment could be, here are a bunch of different estimates for what's going on in the Archean. And the one I will highlight the most is the CO2 concentration. It could have been anywhere from 10 times present level to 2,500 times present level. So this is what we have to work with when we're going this far back in Earth's history. But we can also talk about the other parts of our planet. So the ocean, again, has a huge range of variability of what could happen. I laugh at the salinity one at being from 20 to 50 PSU, because modern Earth is around 35 PSU, or practical salinity units. And again, here on this figure, we have time, where we're all the way over here. And on the y-axis is our temperature of seawater. And the green line is actually a line that's been derived to determine what temperature was tolerable for life over the time of Earth's existence and life existence. And what you see is there's some proxies that end up estimating a higher temperature, but there are also some that end up within the range of what life could be forming in and be happy with. So this Blake et al. 2010 paper is one that you'll commonly see used because it's very close to our present day temperature range, and it falls within this region of what they believe life could have formed in. Then we can talk about land. I don't know how much we can actually talk about the land. We don't know what the shape was, we don't know what the area was, and we don't know how long it was at the surface for. But we do know it exists because we have been able to find very few proxies, but they have been there. We know that there was land. That's about all we can get. So the best estimate we have is that there was about 7% land cover at the end of the Archean, which is believed to have been that first continent that formed on Earth. And the reason why there's not a lot of proxies for this is if you look at this figure, it tells us how old the sea floor is. And as you get to darker colors, you get to older seabed, and the ending of this is just before the time of the dinosaurs. And what you can see is there's not a lot of really dark coloring on this. And this is because a lot of those older sediment has at this point been recycled into our Earth system. And this is why it's really hard for us to get a lot of why it's hard to narrow down that range of variabilities, because there's not a lot, unfortunately, out there for us to be able to pull from what we have. And everything I have shown has been from proxies or from simplified radiative modeling. But something that probably a lot more of us are familiar with is using GCMs, or general circulation models. So you see the first paper coming out of roughly in 2013, 2014 with these Wolf and Toon papers. In these cases, they're using an atmospheric general circulation model coupled to a slab of ocean, but they were using a modern Earth land configuration in their simulations. The 2013 paper looks at what potentially the climate could be. So they tested a warm, a cold Archean climates, and then they also simulated a modern and an ozone-free climate, and we're comparing those side by side to see what the differences were. And the key point I want to take away with this figure is that in their GCMs, they were achieving temperatures that are falling within the range of which we believe the ocean temperatures were. And then the 2014 paper, now that they've established roughly what climates look like, now they wanted to take a step back and be like, okay, how can we counteract this faint young sun problem? And they did a whole suite of sensitivity tests, and ultimately the result they had from that paper was one parameter alone cannot counteract the faint young sun. You need a whole mixture of what's going on to fight with the faint young sun cooling your planet. More recently, with Olson et al. 2022, this paper is using a couple of GCM, the dynamical ocean and a dynamical atmosphere, and they were modeling the Archean with a modern Earth configuration, but also an aquaplanet configuration. And just a little reminder, an aquaplanet in this context is a planet that's entirely encompassed with water. And in this paper, they're looking really at the role of salinity and how that impacted your surface temperature and your sea ice cover. So on the x-axis, we have our partial pressure of CO2 times pre-industrial levels. And then we have ice cover in the first panel and global temperatures in the second panel. And the big takeaway is as you increase CO2, you are decreasing your ice cover, but you're also increasing your temperature, which I feel like a lot of people in this department would like to agree with what she found. So everything that I've said really does play into the motivation of why we're doing this work. And it's because a lot of it's focused on the atmospheric contribution of what was going on in the Archean. There's not really a lot of talk about what the ocean is. Olson et al. 2022 does use a couple of GCM, but they use it to set up the climate. They don't go into the ocean dynamics or the processes that are going on within the simulation. But also, a huge part of this too is before you can make any conclusions about what's happening on the habitability and if life could be on the planet, you also need to understand the dynamics of what's going on in your system. This leads us into the broad question that's been leading my research a lot, is how does ocean properties, circulation, and heat transport behave and change when simulating an Archean-like planet in a coupled GCM. To do this, I've been using ROCKY3D, which stands for Resolving Orbital and Climate Keys of Earth and Extraterrestrial Environments with Dynamics. So very long name, so I will just be calling it Rocky. And this is a coupled GCM that was developed at NASA GISS with a 4x5 degree resolution, 40 atmospheric layers, and 13 oceanic layers. And the reason we use Rocky is because this model was designed for you to break it, essentially. most climate models out there, if you try putting them into these deep time paleo or even exoplanet environments, the models will just break apart and not handle anything. Rocky, they were able to figure out a way to make it be adaptable for all these different environments. So the first Rocky paper you see is the Way et al. 2016 paper where they were talking about Venus. And then you can also see this Olson et al. Paper that I read a lot. She used Rocky in a lot of her work. So now we have the base configuration I was running with for my model. This is heavily based off the Olson et al. With a little bit of changes for what I was doing. So our length of day is at 17 hours. Our planet was spinning faster at this time period. Our insolation is at 1029 watts per meter squared, and this is to account for the faint young sun, so that's at 75% of modern insolation. My atmospheric pressure is at half a bar. My methane is at 1,000 times present level. My CO2 is 10 times present level. Oxygen has been removed. The oxygenation event hadn't happened at this point. CFCs are removed because humans aren't here yet. And then I'm running it with the land configuration. Again, with that 7% land cover, you can kind of use an aquaplanet as a safe assumption of what's going on. But I keep saying aquaplanet, so I feel like we also need to take a step back and look at what's been traditionally done with aquaplanets. So again, they are a planet that's entirely encompassed with water. And the first time you're seeing a couple of GCM with the dynamical ocean was with the Smith et al. 2006 paper, which was quickly followed by the Marshall et al. 2007 and Anderson and Marshall 2009. And all of them were just testing how GCMs and these aquaplanets and idealize things, but I can go into that in a little bit. What we also are seeing in a lot of these simulations, they're using modern orbital parameters and modern CO2 levels. But I want to look more at what the ocean was looking like in these simulations. So to start, they're all running with flat bottom oceans. And if they wanted to change it up a little bit, they were adding a meridional continental strip from one pole to another pole that was 1 grid cell wide. And these traditionally were peaking at about 50 meters above the surface of the ocean. And as one can assume, when you add some things between your ocean, it stops talking to each other, so we're altering our ocean circulations. So in A is our traditional aquaplanet, B is the ridge planet, C is the equatorial gap, and D is our Drake Passage. And all of these are done to very idealize how land could influence what your circulation looks like. So instead of just being like, oh, we're just gonna pick a piece of land here and then figure out everything that went around it, they were instead said, okay, let's look at how land can be distributed across the planet, and that's how all of these different configurations came to be. But one of the first things I learned in my oceanography classes is that bathymetry has a huge impact on what your ocean circulation looks like. And what I have here are just 3 key points of how bathymetry could influence what's going on. It steers our water's flow, could enhance or inhibit mixing, and it also has huge implications for our biogeochemical processes and activity that's going on. Panel A is showing what an idealized case of what your seafloor could actually look like. And first thing I notice is it's not flat. There's a lot of variability of what's going on, but an even better snapshot of what it looks like. B is a cross-section that you can see and see across the South Pacific. And as one can guess, this has a huge impact on what is actually going to look at your ocean circulation. You can get water trapped in these regions where it's lower and water will flow over it. If you are really interested in how bathymetry also impacts this, Liz Maroon does an interesting project with Flatlantic, if you have heard about that one. So, taking this configuration a step further, based off proxies, we're going to be running with 2 different CO2s today, one low at 10 times CO2, the 10 times present level, but I'm also running it with a high CO2, which is 500 times present level values. My ocean depth is 10 of the 13 layers in the model, and my ocean salinity is at 35 PSU, because it falls right in the middle of the range that it could be, and this way I didn't break the model too much that the first time I tried running something. But then also something that is new is this addition of bathymetry. Here are the 4 bathymetries that I have created to run in the model. So to start, we have our flat bottom ocean, which is at a uniform depth, which is why it's all blue. I have my ridge, which is, again, a meridional strip from pole to pole. However, mine is still submerged in the water. It's only peaking at about 650 meters in the water column, or else all the other papers that we can see, they have them fully surfaced above our ocean. Rough is simulating if there was abyssal hills and seamounts in the ocean, so just kind of making the seafloor have bumps to it. And then ridge and rough, I just added these 2 together to create that one. I will sometimes call that combination, so but hopefully I will remember to call it ridge and rough. And I have had questions in the past about this, and yes, my ridge is only on one side of the planet. These are all the simulations I have done to date that are all in steady state. So I have all 4 bathymetry cases here, and then when you're looking down the chart is various CO2 levels, and I've even started some salinity tests as well. And it's important to note that all of these runs took about 1,000 to 3,000 years in model time to achieve steady state. These 500 times cases were annoying. They wouldn't get to steady state for a while. But don't worry, you're not looking at all of these, you're only looking at 5 of them today. So we're looking at the 10 times suite across all of the bathymetries, and then we're looking at the 10 times and the 500 times CO2 cases. And all the analysis I will show is done on the last decade of all of these runs. Going back to the broad question I had, we can now dive in a little bit more into what we're going to talk about today. So first, we're going to talk about how does bathymetry influence the ocean properties when Rocky is configured for an Archean-like planet. And then once we talk about how bathymetry influences it, as you can guess, we're going to go and talk about how do different CO2 concentrations alter these ocean properties on the flat bottom case. And I want to quickly do a little reminder on some of the oceanography terms I will be talking about today. So to start is our ocean properties, where we really want you to focus on this sigma theta here. So this is potential density in the ocean, where potential density is kind of along the same lines as potential temperature, where you're just removing the effects of pressure on your density. So instead of having salinity, temperature, and pressure determine what my density looks like, I now just will have the influence of salinity and temperature on my density structure that you'll kind of, these are modern day Atlantic cross sections of the parameters that I just mentioned. But also it's in sigma notation. So oceanographers only care about what's going on in the tens. So we subtract 1,000 from our density, so it's easier to analyze it. So that's why all of these are at like the 27s, because we got rid of that 1,000 from it. We also have our meridional overturning circulation, where we have 2 cells, where we have this upper cell that sinks in the North Atlantic and then slowly will rise in our Southern Ocean, and then it'll kind of circulate through, or it will come and sink around Antarctica and travel back up into the North Atlantic and kind of follow us. So we have our upper cell and our lower cell on modern Earth. And lastly, some figure I think almost everyone has seen before in their lifetime in this field. I want to focus quickly on our ocean, where we are peaking at about 2 petawatts, and we see this very symmetric meridional feature that is showing that there is poleward heat transport across the planet. So the first question is, how does bathymetry influence what the ocean looks like? And again, we're looking at all 4 cases in this. So to start, we're looking at our zonal mean potential density, where these are all averaged over longitude. So on our y-axis, we have depth, and on our x, we have latitude in all the cases. Lighter colors are lighter densities, and darker colors are higher densities. And one thing that you can kind of take away from this is they all look really similar to each other. So to make it easier for us to analyze, we have taken a difference of them. So it's flat minus the bathymetry. So in these blue colors, you have that the bathymetry has denser water, and in red you have that the flat case has denser water. And one thing to note is when you're looking at the flat case, you see that there's a strong density gradient at around 40 degrees north in latitude. But you also see that there's these huge bands where the flat is denser in our ridge cases. And what this is showing us is that there's this expansion of this bowl structure here, and it's actually expanding to be more poleward. So you're not seeing the same temperature gradient until you're closer to 75 degrees in latitude. And our rough has the same structure, but it's at a lot lesser of an extent. And this is really a strong feature from what our ridge is showing. We can also look at salinity, because as I said earlier, we know that our salinity and temperature will play a role in what our density is doing. So when we look at salinity, so here we have our salinity, and the differencing again will be bathymetry saltier in blue and the freshest saltier in red. You see the same exact structure come out of it. But in this case, you can actually see I think you can see easier in this one. Once you get to the height of the ridge, so this is the 600 meters here, and the ridge was at 650, you can actually see that the water appears to be getting trapped in these ridge cases, which is making it saltier at depth than if you were higher up in your ocean. But again, you do see this poleward expansion of the water becoming pressure. And then we can also look at our potential our potential temperature, which I would like to point out, it is between -2.4 and -1.4. It is a extremely small range of temperatures at this time in this simulation. So in our blue, we have our warmer bathymetry, and in red, we have our warmer flat. And again, you can see the same exact structure. We have this poleward expansion of warm water. The salinity and temperature behave oppositely when you're looking at how it influences density. So this is really interesting that in all cases you are seeing these features pop up. But we want to look at how these actually could be varying. So we decided to plot histograms of the 3D counts of what's going on. So these are counts of potential density, salinity, and potential temperature over latitude, longitude, and depth. And one of the first things that I noticed when I saw these is that my potential density and my salinity are following a very similar pattern, and it appears to be a bimodal bump in both cases. But also, I noticed that this, again, is confirming our potential temperature is falling in a very narrow range of what it could have been. And I laugh at this count of how different they are. But going back to the density and the salinity, is you can also see that in the ridge cases, they're peaking at lighter densities and lower salinities in that first peak of the bimodal distribution. But our flat and our rough case are actually peaking at the higher end of these values, which is an interesting feature to see. And the reasoning behind this is when you look at that density structure and that salinity structure, there is that expansion of the poleward, that poleward expansion of the lighter water. So you would expect to see that at the lighter values, you are seeing these lighter densities peaking. And because of this, and because of how these distribution looks, we're inclined to say that the salinity is driving what our potential density structure looks like. But I also want to take a second does anyone think they know why this is happening that hasn't seen this presentation yet? Well, you can probably guess. It is because all of these simulations are entirely ice covered. Which honestly, I wasn't fully expecting it to be completely ice covered, so this was kind of a fun result to find out. So now we know what's going on with our density. We have an idea of why it's structured the way it is. And we can start to try and pull apart what's happening in our ocean circulation as well. So I went ahead and drew what I believe is happening in our circulation, where we have our light water rising in the equator, moving poleward and then sinking at about 50 degrees, and then moving back towards the tropics, and then you have these cells. However, you have similar structure and overturning and circulation in your ridge cases. However, based off where this gradient is, I believe it's shifted more poleward. And this will follow through with what you see in the rough and then the ridge and rough too, based off where these gradients lie. So here we actually are plotting the stream function in sphere droops, which is 10 to the 6 meter cubed per second, so it's just a volume flux of what's going on. And in red, you have clockwise rotation or circulation. And what you can see is, I guess, mostly right as to where the circulation is. So you see very symmetric cases across all 4 of them. And you do see that we are seeing this downward, or this downwelling happening at near 50. However, in our ridge cases, you can see that this has actually become more localized to where the ridge peak is. And again, about here is where the ridge would be peaking, and this is kind of water and how that circulates here. We can also look at the heat transport and how this is factored into it. And overall, you can see all of them do follow the similar pattern of what we saw on modern Earth, with just a poleward heat transport in both hemispheres. So this would be moving to the southern hemisphere, the South Pole, and this would be moving to the North Pole. However, we are seeing weaker heat transport overall, because we were peaking at 2 petawatts on modern Earth. This is only peaking at a little under 1. So, from what we found in the bathymetry is that our potential density differences are primarily driven by our salinity. Our ocean temperature is cold and homogeneous with that 1 degree difference across the planet. Our presence of the ridge is shifting our mark poleward and intensifying in the middle of the water column. And then we have a weaker oceanic heat transport compared to modern Earth, and this can be linked to just the fact that we have a colder ocean and potentially linking to our weak temperature gradient, or meridional temperature gradient. Question 2 is then taking us into our CO2 concentration. In these cases, again, I'm looking at the flat 10 times and the flat 500 times CO2 values. So we'll start with the density structures again. And again, these are all the zonal means where we have, for our average over longitude, depth is on our Y and latitude is on our X. Lighter colors are lighter densities, darker colors are higher densities. And I don't think I need to take a difference plot for you guys to see the difference between what's going on here. We have a complete reversal of our density structure on the 500 times case. So instead of having our light density to our heavier densities, we are now going from our heavier densities, and poleward is our lighter densities. So again, we can look at salinity to see how that compares, and see the same exact shape and result of the reversal. So the lighter colors are our lighter density, darker colors are our saltier water. And yeah, sorry, I laugh whenever I see these figures sometimes. They're just insanely different in what they look like. So yeah, so you end up, instead of fresher to saltier, you end up with saltier to fresher. And then to finish, what we could look at for what they look like, we can see our potential temperature, where they have to be on completely different color bars because it is extremely different oceans. So in our 10 times case, we had that really small temperature range, but now in our 500 times case, we are at 0 to 40 degrees Celsius in what our ocean could look like. So we can look at our histograms again. Again, these are 3D counts, so over latitude, longitude, and depth. And I'll go through these each one by one because they all have different features going on in them. The first one is our potential density, where we see that the flat times the flat 10 times compared to the flat 500 times, we see that there's been a shift in what our distribution looks like. And there's also been a slight broadening of our densities, where before we were at about 24 to 32 kilograms per meter cubed, now we're at 19 to 29 kilograms per meter cubed. So this slightly broadened out in the ranges that we're covering. Our salinity has also broadened out, but we now have a huge, we have a lot of values higher up at higher salinities. And the interesting thing with this is when you have higher salinities, you would expect to see higher densities, but we're not. We're seeing these lighter densities. But then we can, but this actually plays into what's going on in our ocean, is our ocean has completely warmed up. And because of this, the temperature warming and broadening out and not even being close to where it used to be, when you warm your ocean, you're lightening your water. So because of this, and it leads us to thinking how, in this case, we actually have potential temperature driving what our density structure looks like. And this is why. We have completely removed all the sea ice. In the 500 times CO2 case, our sea ice just isn't present, which makes sense. The planet got very warm. So now we can look at our ocean circulation. We saw what this 10 times case looks like. However, in the 500 times case, I am expecting to see a complete reversal of what's going on. So now we're going to have sinking motion in our equatorial region that then moves pole, then at depth moves towards the pole, and then rises closer to your pole, and then once it's back at the surface, will move closer to your equator, which is a complete reversal of what's going on. And when you plot the stream function, again, these are going to be on different scales, because if I put them on the same scale, you would not be able to see the flat times circulation going on. We saw this one already, so we know what to expect for that one. However, when we're looking at the 500 times case, we do see this reversal happening, where we now have really strong downwelling at about 20 degrees north that then comes back up, and it's amazing how cool that looks. And this can also be taken a step further into looking at our heat transport, where we are now at a heat transport in our 500 times case that is peaking at about 6 petawatts, and it's primarily northward. And it really does line up really well with how we should have convergence of heat popping up right around here. And last but not least, we have coupling in our simulations when we include enough CO2. So what we have here is our atmospheric stream function, and at the bottom is our oceanic stream function. And really, this is just showing how different these mechanisms can be. With this ice covered here, there is really weak overturning going on. However, when you remove the sea ice, the atmosphere and the ocean are allowed to talk to each other and have really interesting features coming out. Like one feature I will bring up is right here at this 20 degrees north. That's where we were seeing that really strong salinity peak, which when you look at the atmospheric circulation, you would expect high evaporation happening right here. So it's kind of cool that you can start seeing these features come out and how they feed into each other. So with the CO2 concentration, we can see that our potential density and our salinity experience a complete reversal of their spatial pattern. When you're at the 500 times CO2 case, our potential density is driving what our potential density is being driven by our potential temperature. And something that I didn't really think my research was going to go towards, but it ends up being kind of fun to look at, is how when you are running these simulations, we start opening up the idea of an ice-covered versus an ice-free planet, and how all of these can change what is going on your planet. We also saw that we have a strong salinity and potential density peak aligning with that strong downwelling at about 20 degrees north. And that we saw that we have an oceanic heat transport that's larger than modern Earth. And I opened this. You end up with a warmer ocean and a larger meridional temperature gradient, which then can feed into how strong your oceanic heat transport is. But naturally, there are caveats to running models. One of the first being is Rocky 3D is a very coarse resolution model, and because of this, we're losing and not resolving a lot of the smaller scale features, which would be really cool to see at some point, but we're still just gonna roll with Rocky that time. We also are not able to alter diffusivity, geothermal heating, and tidal forcings, because we believe these all could have huge implications, especially the geothermal heating could completely change what that 10 times CO2 case could look like, because you're adding in heat from underneath the ice instead of from the top of the ocean. And then something else that you'll see in literature when we talk about Rocky, and this is actually something that gets, depending on what papers you use, if they'll bring it up, is that if you have enough methane in your atmosphere, you can start creating an organic haze, which would act as a cooling mechanism on your planet. And Rocky doesn't have the chemistry required to achieve this, so unfortunately it's not something we're able to include. However, Rocky's getting an update. Makes me very happy. I've been complaining about it for a while. We're going to be able to add geothermal heating into our ocean, as well as changing the mesoscale diffusivity, and they're going to improve the sea ice thermodynamics and dynamics, and if anyone's ever walked into my office, I guarantee you they've heard me complain about that before. So, I'm very excited about that. And next up, I'm going to, as you saw, I had that huge table of simulations at the beginning of this talk, where I'm going to finish off my 500 times CO2 bathymetry runs, and then start the salinity and ocean depth sensitivities. So our salinity is just kind of going at the potential range of what it could have been at this time period. And then the ocean depth is something that I'm just interested in looking at, because a lot of papers will either run it with a really shallow ocean or just cut it at the 10 layers. So it'd be interesting to see how the shallow ocean will play a role into this, but then also how a deep ocean will go into this. But I'm scared to do this one because it's going to take forever to get to steady state. But I would also like to just quickly acknowledge the Advanced Opportunity Fellowship and the Wisconsin Alumni Research Foundation for funding the work I've been doing. Huge thank you to Hannah for dealing with me. And then a huge thank you to Dan and Myra for being on my GAC. And then also Liz for helping me try and understand stream functions better than I thought I could. And Pete for helping me build Rocky 3 different times, so it might become a 4th time. So yay! Then also just a huge thank you to all of the friends I made here at Madison, but also I have a handful of friends I know that are watching online, so I greatly appreciate all of you. And then my family that's also watching this, probably yelling at cats for trying to jump up through the TV, but thank you for watching this, Mom and Dad. But most importantly, my cats. Oh. Rhapsody and Blue. They're my little Furbies. So yeah. So with that, we'll take any questions.
All right, thank you, Phil. We'll start with students, as we always do. Do you have questions? Go for it, man.
Yeah, I think so. It's a really cool talk. Have you looked at like 2D maps of when you're at a region? Like surely you start to get boundary currents and things that force things more polar. I wonder if you've looked at the spatial nature of that.
Yeah. So this is the bottom circulation that you'll see in it, and yeah. I found the figure. What was your question again? I'm
Well,
sorry.
it's kind of exactly this. It's like when you're at a region, do you see that?
Yes, you definitely, it's still very zonal flow, and that's just how aquaplanets are. Like, there's basically no movement when you're in the flat cases. But yeah, when you are with the ridge, you do see these meridional features coming out. So yeah. And they actually do get propagated upwards into the top of the water column. It's not as strong, but there's tiny little meridional motion at the surface as well. So you do see it. Greater.
Great talk, Marissa. I had a similar follow-up thing as to what Hamish just pointed out. I'm pretty sure you had millions of other figures to show, but it would be cool to see that if you pick one particular latitude and then go longitude and depth, and then start from -30, 0, 30, 60, 90, and that might probably help us understand why that shift in density happens just visually. I know you know why the shifts are happening, but visually it might be interesting to just see like across latitude and then longitude.
Yeah.
So here's a ridge, here's
Yeah, I haven't really thought about doing it in that cross section way, so yeah, that would actually be really cool to see what's going on in that way. Yeah.
but amazing talk.
I think my threats are working.
Nicola?
Yeah, I have a quick picky question. So at the beginning, you show the range of every different parameter that you could have chosen, which is all very large range. And especially the methane one, I think is like 10 to 10,000 present
Yeah.
levels. And if my memory is correct, like methane is have a very high greenhouse gas effect. So why did you pick to look at CO2 and not methane when the range of methane was higher and probably also greenhouse effect was less?
So I picked the CO2 because a lot of when we were thinking about creating this project, we were really looking at that Olson et al. 2022 paper, and that work really focuses in on how does CO2 play a role in that. So that's why we decided to use the CO2 is that was connected with what Olson did and how we can compare between the two of the projects. What's going on. But I think it would be interesting to alter the methane as well, but I don't know if I want to complicate the matrix more than it already is at the moment. But yeah. I can teach you how to run Rocky and you can do it. Yeah, Jack.
My question is just kind of about Rocky, and when you're saying run Rocky, like, what is the level of interaction that like the atmospheric component has with the ocean component? And I was really curious about that, like when you have your fully ice covered simulations, like does that really limit like the impact that like those two can have when like talking to each other again?
Yeah, so I'm not that familiar with how they are coupling the two of them, but I would have to look more into the literature of how they're coupling.
Yeah, no worries.
Yeah, Dan.
And actually, a follow-up on that, the answer could be the exact same, but do you have any idea how does ice move at all?
I'm not sure if they go into that actually in the paper, because a lot of the sea ice stuff in the paper that I'm thinking about when Rocky came out got like a little bit on it.
They can. The ice can move, but in these simulations, it's really thick ice, so it's like a cap. Yeah.
Have you looked at how thick it is?
Very.
Yeah, some regions you have like over 100 meters of sea ice.
That's why we don't trust this model sea ice.
Yeah.
So I mean, in that sense, you get this kind of cool set of two experiments where in one case you have an opportunity for momentum coupling, and in another case you have purely a buoyancy driven. So it's kind of neat. You see, look at the fluxes. I think the addition of that geothermal, like that seems like the coolest thing to add rather than any other.
Yeah, I'm very excited about the addition of that to the model. So, Till.
Yeah, so to follow up on that, I wonder whether, because, you know, like in the ice covered situation, right, you essentially, the atmosphere becomes irrelevant.
Yeah.
In the flat case, you also don't have any zonal variation. I wonder whether it might be worth considering just a much simpler model, right, where you literally just have one zonal strip, and I wouldn't be surprised if you should be able to reproduce exactly the same flow patterns.
That would be interesting to try and do.
I had that thought. I actually had that thought.
And then,
Me too.
and then you can run gazillions of.
Right.
Yeah. Angela?
That's related to my question. So you have plans to test the variations in salinity and how you think that might impact. And so, yeah, just kind of a clarification question on that. Because you had to increase the CO2 so much to be able to have that, or the ocean atmosphere interaction. Are you going to be testing the salinity experiments on that high
Yeah.
CO2 run?
I'll be testing them on both the CO2 ranges, so at that 10 times CO2 and at that 500 times CO2.
So this is just a totally naive question from my part. Do you have a hypothesis then on, do you think that'll have a really drastic change in the same way that the CO2 did? I'm just
Yeah.
curious.
Yeah, so I think the salinity is going to have a really cool impact on it because there has been literature out there before about how salinity alone could reverse your ocean circulation. But usually those papers have a salinity at about 260 PSU when they see that reversal. But I saw that reversal here with a salinity that is peaking at like 45 PSU. Now that was being really driven by our temperature of the ocean. So I think it will be really cool to see that if I'm able to achieve that reversal, at least in like the 10 times case, because then it'll kind of show us if Rocky's just kind of being special in how it's handling different things. Yeah, John.
Yeah, Marissa, really interesting. Congratulations on good work. I don't know anything about the ocean, so.
That crash course was for you, Jim.
It was really good. It was really good. How in the world does the ocean create salinity gradients? You're not adding or subtracting salt in your experiments, right?
Yeah.
So how do you create the gradients when you start with a flat gradient? What's doing that?
Give me a second, I gotta find it. So, in the case of the in the 10 times CO2 suite that I was showing, I really think that just came down to just how the water is moving around and how water gets trapped around the bathymetry, and that's how you get it in the 10 times cases. In the 500 times case, this is a precip map where what you see is I have a really strong precipitation band here and really high evaporation up here. So the ocean is actually helping to enhance how salty my ocean becomes because we're taking water away from the ocean and the salt's being left behind. So that's how I believe that the ocean gradient becomes.
Yeah, so how do we get salinity gradients in the water ocean? Like, not the gradients, but just like differences across things, like what happens at the poles versus what happens.
There's a lot of things that could be doing that. I don't know. Like at the pole, you have the formation of the sea ice, which would be the brine rejection, which would be kicking out your salt, which makes the water saltier.
Saltier, that high level.
And then it would be causing that sink and causing it.
The oligotrophic subtropical gyres, those are really salty or fresh.
What first word did you
The
say?
oligotrophic subtropical gyre. So like your standard subtropical gyre, right, that sits in like, the North Atlantic or something, is that salty or fresh?
I haven't talked about modern ocean in dude.
That's all right.
I'm like completely.
It's related to that.
Yeah, it's.
So the subtropics, so not the tropics, right? So the equatorial region is fresh, right? And the subtropics are salt, right? Because you've got
Evaporation.
right.
Okay.
It's the what
I
branch
did-
of the Hadley cell.
The descending branch.
Yeah, there you go.
Sorry. She knows
All right.
this.
Okay, then if I could follow up. In the 500 times CO2, any peaks at the atmosphere are since the oceanic heat transport exceeds the current day, that means that the burden's off of mid-latitude cyclones and tropical cyclones comparatively. And so are they more sluggish, less frequent, or only episodically as strong? Do you know?
That's great. I mean, I haven't really looked at the atmospheric heat transport as much as I've looked at the oceanic one, so I don't know if I can answer your question.
And it doesn't necessarily mean that the ocean does more heat transport than the atmosphere in that case. It just does more relative to what the ocean does in modern day.
But they're close right now. They're 30, 40, I think.
Yeah, in
Right,
the
so-
equatorial region they're close.
Well,
And then the
globally,
mid-latitudes kind of take it.
Okay. Thanks.
So I think Myra has a question, right?
Yeah, Myra has a question online. Can you potentially expand your study to look at habitability predictions in exoplanets, even with the limited observational data? So it's just curious if you've thought of how the outputs of your research may be linked to habitability potential.
Yeah, so one of the big things that I can think about how it could impact the habitability is, and it might make people happy, is like, at the moment, I don't know, I can't make any really strong conclusions that bathymetry is overall impacting what the climate looks like, which makes me sad, but I also am like, someone in a couple years doesn't have to spend 2 years trying to figure out how to run a model to create the same result. But, can you repeat that first part of the question? Sorry.
Can you potentially expand your study to look at habitability prediction in exoplanets even with limited observational data?
So for this work that I'm trying to focus on, it would be hard to expand into the ocean what we have determined because you can't detect if there's ocean on other planets at the moment. So I could take what we know about atmospheres and apply it into these models and kind of figure out what's going on in that sense. But from an ocean standpoint, it's also kind of hard because salinity is completely different potentially is different on other planets. Our equation of state in the ocean is completely empirically derived because we can't directly make those calculations. So it would be nice to be able to say I can, but with an ocean focus, I don't know if it's necessarily like the easiest connection to make at the moment. But in the near future, it should be able to be done.
Just like looking at this plot, just looks like you have like a perpetual monsoon in the southern hemisphere. If you go back to the ocean temperatures, like is the northern hemisphere ocean colder in the 500 CO2 case than the southern ocean? Right?
Give me a second, we gotta get, yeah, it is.
Yeah.
You end up with a larger temperature gradient here.
Yeah. What do you think is why do you think that happens?
I honestly don't really know why that's happening.
Is there eccentricity in the model?
There is. There is. It has like so it's obliquity eccentricity or like modular. So we didn't put it at 0, and so like here it's going to be some hemispheric asymmetry.
Yeah. I wonder if it's an eccentricity thing or something.
I think you might be right. Tim brought this up the other day too.
Yeah, well, that's interesting because then you just get, that's probably what you get, that single habit.
Yeah, it'll be interesting to see if you do it the other way, when you have like the Archean Eon with southern hemisphere pointing, if you actually get a shift of the whole nest to the southern hemisphere.
Dan?
The flat 10x and the flat 500x here, are those both initialized without any sea ice?
Yes.
Okay. It'd be interesting to see whether you take run a restart on your flat 10x, do you think you'd melt the ice?
If I put it into the 500 times case?
Yeah, like adding 50 times CO2, or are you at a point where you're at a stable equilibrium at that point, just because of the albedo?
I mean, it would be interesting to try and do that, but yeah, I'm not.
You could probably do the reason why I'm asking is it'd be really interesting to see how the ocean goes from sort of just a diffusive kind of chunk of water to a active circulation.
Yeah, the 100 times cases are still fully ice covered. Like that's the thing with this model is it just wants to stay ice covered and cold, and that's where it's like.
But there's going to be a region of stability here, right? Because you have snowball Earth instability here. So I don't know whether those are on the side of the bistable regime or in the middle.
The 250 has this just a weird block in the northern hemisphere of ice, right? So it keeps trying to do it 500 times with the case where we're like fully ice free, and so we wanted to look at that too.
But that's kind of why I was like sort of getting at the idealized model, because then you can really dig into the mechanics of it and extract what exactly is happening, and like there's so much here in this model that you don't actually use, right? So, and it produces a lot of noise and makes it very difficult to do these integrations, and you have to babysit the model for weeks on end. That's true.
Other questions? No, it's fine. I actually think I have really been thinking about that too, because I was like, I thought this would buy us more than what an idealized model would originally, and I think what we're finding out is that it doesn't necessarily, at least for like the kinds of ocean type questions you want to answer, and I think that's a big takeaway from this is that this model, was designed to kind of think about exoplanets or early Earth, but it didn't really actually think about the ocean or the ice in that process. So.
I mean, an idealized model has also the benefit potentially of giving you a sense of whether you're in the right ballpark here, right? Because that's so hard to know. Whether is your energy computed, like your energy balance at the surface computed? Is it realistic to have 100 meter sea ice, etc.?
All right, other questions? Are we good to go? Actually, I have a meeting at 1, so no, you're done with your questions. Thank you.